start our lecture. So yesterday we talked about testing hypothesis. So we have to know what a hypothesis is. So usually it's something concerning about the parameters of the distributions. So these are the two that we are interested in. So we set a hypothesis. There are two. One is the null hypothesis, and the other one is the alternatives. So, for example, we want to know whether mu equals 0 and mu greater than 0. So we have to decide on which one we believe. So naturally, the statement is concerning about mu, so naturally we will take the sample mean to have some idea what mu is. So we look at the difference, all right, mu x bar and mu naught. So if the difference is big, so it's likely that maybe mu does not equal to mu naught, all right? But this difference depends on not just the magnitude. The magnitude itself is not good enough to tell us whether mu is different from mu naught, because it also depends on the variation of the x bar. So we have to divide by the standard error of x bar. All right? So what is standard error of x bar? So it will be sigma over root n if sigma is known. If we know the sigma. All right? Then, so x bar minus mu naught is big. So if you adjust by the standard error, if this is big, all right, then we consider maybe there's evidence to believe that mu is really different from mu naught. The idea is that if mu is equal to something which is greater than mu naught, then we expect because we expect our x bar is equal to mu. If this one is much bigger than mu naught, then we expect this will be very different from mu naught. And we adjust by the standard error. All right. So now the question is, how big is this considered as big? So that's why we need to know the distribution. Let me call it Z. So what is the distribution of Z? All right. Does Z follow a standard normal distribution? Is this correct? X bar minus mu naught. All right, of course, this is under the null hypothesis, under the assumption that this is true, or mu equal to mu naught. Is this correct? Yes? No? I don't know. Huh? Correct or not? Does this Z here follow a standard normal distribution? No. Why not? Okay. We are not sure whether this follows normal distribution or not. We need some additional information to decide whether this is normal or not. What are these additional information? The sample, x1 up to xn. If they are from normal distribution with mean, mu, and variance sigma square, then this is correct. All right? Or sometimes we even accept that if this is approximate normal, not exactly normal, but close to normal, then this is also correct. All right? But what happens if we don't have this information? All right? Is this correct? So this not exactly correct, but we have this very powerful theorem called central limit theorem. So if n is big enough, then this Z will be approximately normal with mean 0 and variance 1. All right? So my point is, okay, the train of thought is like this. We start a statement with mu equal to a certain value. So in order to check this statement, we look at x bar, which is our information about mu. So we look at the difference between X bar and mu naught. Mu naught is the value of mu under the null hypothesis. So if this difference is huge, we suspect that mu is not mu naught. Mu does not equal to mu naught. But this magnitude of difference depends on the standard error of X bar as well. All right? Not just how far the mu from, how far the mu is from mu naught, but also depend on the standard error of X bar. So we have to adjust by the standard error of X bar. So we come up with this test statistic, X bar minus mu naught adjust by the standard error. So the next question is, how big is considered big? So we need to know how this X bar minus mu naught over sigma over root n behaves. So this follow a certain distribution. So the question is, what is the distribution? So we need more information. Either the underlying population, the x1 up to xn, is a normal population with mean mu and sigma square as the variance, then this will follow a standard, then this Z will follow a standard normal distribution. All right. We also accept that if the underlying distribution x1 up to xn is a sample taken from an approximate normal distribution with mean mu and variance sigma square, then this is also the Z. Then Z is also not follow a standard normal distribution. So what happens if we don't have this information, not even approximate? Then what is the distribution of this Z? So by the central limit theorem, if your sample size is big enough, so as a rule of thumb, we have sample size bigger than 30 is considered as big. All right. But I have the word of caution, the approximation will be better if your sample size getting bigger. So for small sample size, or maybe 30, 31, compare with n equal to 100, of course the approximation with a sample size of 100 will be better. All right? So by the central limit theorem, if your n is big enough, then Z follow approximately normal distribution with mean mu, mean 0 and variance. Oh, I'm already divided by root. So with standard deviation equal to 1. All right? So the idea is something like that. Then how big is big? So since we know that it follows this distribution, so we will think that it's big if Z, the observed Z value, the observed of Z value is bigger than Z alpha. So if alpha, let's say 0.05, then this number is 1.645. So in other words, we take a sample, calculate the X bar, and then substitute here, calculate the Z, I call it Z observed, which means that it is observed from the sample, the value observed from the sample. We calculate the test statistics value observed from the sample, and if this value is greater than 1.645, what does that mean? It means that for a standard normal distribution, 1.645 is here. The chance greater than it is 5% chance. So this is the region. So if my Z observed falls somewhere in this region, I will reject the null hypothesis. All right. What does that mean? It means that I make the decision based on what I see. So I see that this Z observed from the data or from the sample is bigger than 1.645, which is considered as quite big. All right. So in that case, I reject the null hypothesis. I conclude that mu is different. The mu, the actual mu, is greater than mu naught. It does not equal to mu naught. It's greater than mu naught. All right. So that's the idea. But on the other hand, if my alternative is mu that's less than mu naught, then I expect that X bar should be less than mu naught. So it's much smaller than mu naught, then I will reject it. So I will reject the null hypothesis if the observed value is less than minus 1.645. So in other words, I will consider rejecting the null hypothesis and favor this alternative if the observed Z value fall on the left side of minus 1.645. All right? So that's the basic idea. So from now on, whatever hypothesis concerned about mu and sigma square, the idea will be similar, except that for hypothesis concerning about variance, we have a different way to deal with it. All right, but while for the mean, basically it is standard normal or the t distribution. All right. Now here we make the assumption that sigma is not known. Is known. All right. What happens if sigma is not known? Then what to do? So because sigma is not known, we cannot use this test statistics anymore. So we have to modify it. So we will use this x bar minus mu naught, but we estimate this quantity from the data, from the sample. So we'll use the sample standard deviation to estimate the sigma. So again, if this is too extreme, then we'll consider rejecting the null hypothesis. So if the alternative is like this, so we'll consider rejecting t if it's the observed t is too big. But how big is considered too big? So it will be a t n minus 1 alpha, all right? That is the number taken from a t distribution with n minus 1 degrees of freedom. This is the point where the chance bigger than it is alpha. All right. So this value depends on two quantities. Depends on the sample size minus 1, and also depends on the alpha. Alpha is the level of significance, which means that the probability of committing a type 1 error. All right. So that's what we are going to. Yes, so this is where we stop. So we'll continue with this part when sigma is not known. Okay, so hypothesis testing on means with variance unknown. So we want to test some statement about mu, and variance is unknown. And here we assume that the population is normal. All right, so we can refer to section 6.3.2 as how the test statistics as well as the distribution of the test statistics derived. Okay, so suppose we want to test this hypothesis, mu equal mu naught against mu does not equal to mu naught. So we let this be our test statistics. So basically, I replace the sigma by S. Now, remember, if we know sigma, we know the population variance, sigma square, we should use sigma. If we don't know, then we have to get it from the source. I mean, from whatever we know. So what we know is from the sample. So we use the sample standard deviation to estimate sigma. Okay, so now it looks as if we replace sigma by S, but because of this estimate sigma by S, so now the distribution of this T, all right, the distribution, so what is the distribution? All right, this one does not follow exactly a standard normal distribution. In fact, we discussed it in the last chapter. This follows a T distribution with a degrees of freedom n minus 1. This is important because we have to address the question whether what we observed from the data when we calculate this T or observed T, whether it's too extreme or not. If it's too extreme, we will reject the null hypothesis. So how do I know whether it's too extreme or not? I know how this T behaves. It follows a T distribution with n minus 1 degrees of freedom. Therefore, I just compare with this distribution. Then I know that what I observed is too extreme or not. So that's the idea. Okay, so we will make the decision when the observed T is less than this number, or greater than this number, or less than this number. So in other words, this is the T distribution with n minus 1 degrees of freedom. These are the two numbers, T n minus 1 alpha for 2 and minus t n minus 1 alpha over 2. Because the t distribution is symmetric about 0, so this is the point where greater than this point with probability alpha over 2. So the negative of this value, that means this point, the chance less than it is also alpha over 2 because of the symmetric. There's a negative sign here. All right? So now the idea is very simple. Get your sample, calculate this t. I call it observed t value. If the observed t value is somewhere here, then I do not reject the null hypothesis. What it means is that based on this sample, this particular sample, what I get is not, I still find that it's not sufficient evidence to say mu is different from mu naught. All right. So therefore, I do not reject this statement. All right. From statistical point of view, when I say I do not reject mu equal mu naught, all right, it means that I don't have evidence to reject it. All right. So I cannot do anything. I just have to sort of accept it. All right. But it does not mean that this is the true answer. So what I'm trying to say is that, okay, this statement is true at this point because I don't have evidence to reject it. All right. So for example, if I go to a park, I don't see any bird there. Then I say that, okay, there's no bird in this world because I look at the park. This is my sample. There's no bird there. So based on the information that I have, I don't see any bird, so I will not reject this statement. But once I see one bird, then I will reject this statement. So in other words, based on the sample, I do not reject it. All right? So, but it does not mean that the statement is true. It simply says that I do not reject it. So in practice, we just use it or accept it. All right? So my point is, based on the sample, we make a decision. And the decision may be wrong. In other words, we still don't know the true answer. We just say that, okay, I don't have evidence to reject your null hypothesis. So I keep using your null hypothesis statement until I found until I find evidence say against it. All right. So for the one-side test, okay. So yeah. So this one, if my observed value falls here or falls here, fall within this region or this region, I will make the decision to reject it because this is considered as too unlikely to have such values if mu equal mu naught. All right. So it must be mu different from mu naught, either bigger than mu naught or less than mu naught. All right. Okay, for one side test, that means one side alternative. For example, the alternative is mu bigger than mu naught. Then we'll reject the null hypothesis if the observed t value, this is the observed t value, greater than the t n minus 1 alpha. All right. While for mu less than mu naught, then we just reject it when the observed t is less than minus t n minus 1 alpha. Okay. So this case, t n minus 1, so we will reject if you force here where this is t n minus 1 alpha. So this area is alpha. While for this alternative, you are not looking at this side, but instead you are looking at this side. This value such that less than it with probability alpha. So this value is minus t n minus 1 alpha. All right? Okay, let's look at an example. So here we have this link, the average length time for students to register for summer course at a certain college is 50 minutes. So we try something new. So this is the status quo. The time taken or the average time taken to register is 50, but now we have a different procedures. All right, we want to try it out. All right, so we select 12 students so that their registration time is noted or record, and then find out that the average is 42, while the standard deviation is 11.9. All right. So in this case, we have a sample of size 12, and x bar X is the time for registration, to complete the registration. So X bar is 42 and S is 11.9. All right. So we want to test the hypothesis that the population mean is now less than 50 minutes using a level of significance of 5%. All right. So this is the hypothesis that we want to establish. So in other words, we want to test mu less than 50 against mu equal to 50 based on the sample of 12 with sample mean 42 and sample standard deviation 11.9. All right. Now, so as I said, so we use X bar minus 50 over S over root n is 12. Consider this test statistics, whether it's too big or not. So what is the distribution? So the distribution is n minus 1 with the assumption that the population of this registration time follow normal distribution. That's an important assumption. All right? What happens if this is not, we do not make such assumptions? So what is the distribution of this? Does it follow a t distribution? We're not sure. All right. Because the underlying distribution is not normal. All right. But if we believe that the underlying distribution is close to normal, we can still use it. All right. N is big or not? N is 12. Oh, yeah, if N is bigger and we don't know the underlying distribution, can we conclude that this test statistic T follow a T distribution? Okay? Okay, it's not so clear. Okay, strictly speaking, you need the underlying distribution to be normal. And once the underlying distribution is normal, then this test statistic X bar minus mu naught or mu over S over root n will follow a T distribution with n minus 1 degrees of freedom. Doesn't matter what your n is. All right, even n is 5, it still follow a T distribution. But on the other hand, if your n is very big, even for example 100, then the T distribution with a degrees of freedom 100 is already very close to a standard normal distribution. So it makes not much difference. But strictly speaking, it does not follow a T distribution. Then, from another angle to look at it, if n is 100, then this central limit theorem saying that this X bar will follow approximately normal. All right, I did this X bar minus 50 over sigma over root n. Sigma, not S. So will follow approximately standard normal distribution. All right, but there's still a gap between sigma and S. But there's this law of large number, all right, saying that yes, if your sample size is big, but we don't know how big is considered big, you can consider 100 as big, then this S square should be quite close to sigma square. So in that case, so we have a few layers of approximation, so this quantity is still follow, you can treat it as standard normal. But only an approximation. How good the approximation, we cannot say. All right? So we can still use it. All right? Okay. So we make such assumption, it solves our problem. But in practice, you have to ask this kind of questions. All right? Whether you make such assumption, whether it's justified to have such assumption, normal assumptions. All right? So we follow what we discussed in the previous examples or session about when testing the hypothesis of mu with sigma no. So first of all, the first step is to set up the hypothesis. So please don't just write down the hypothesis mu equal to 50 against mu less than 50 without telling me what mu is. So you have to say that, okay, mu, we are considering the mu which is the average registration time, all right, for the whole population, student population. maybe in certain university or certain faculty or certain department, but this referring to the mean registration time for that population. All right, and since less than 50, yeah, okay. It may be arguable, but here it stated that we are interested in testing whether the new registration method has a shorter registration time. So the alternative hypothesis mu less than 50. All right. But what I want to say is that even if you're not given that, all right, you're not given that the last second line less than 50. Come to think of it, you have a new registration method, like your new luminous, right? So what you want is that new procedure should be better in the sense that the registration time should be shorter. So in other words, you want to find out whether this new registration method has an average mean time equal to 50 against less than 50. You don't bother to test a new registration method with a mean time greater than 50. So the alternative should be mu less than 50. All right? So my point is, not every time you are told what to test. You have to decide based on the nature of the problem, what is the alternative. So, of course, if it's not clear which direction to go, then your alternative is not equal. Otherwise, you have to make a decision. And also, you have to, for hypothesizing, you have to specify what is the chance that you commit type 1 error. So in this case, it's 5%. So what we have done, we're going to accept a risk of 5% rejecting wrongly the null hypothesis. All right, so here, so we set mu equal 50 against mu less than 50. The step 2 is to set up your significance level, the type 1 error chance, the probability of committing a type 1 error, 5%. Then next, set up your test statistics. So because it's unknown, so this is our test statistics. And not just the test statistic, you also have to specify what you're going to do. So at least the old approach is to specify your critical region. So in this case, I set up the critical value 1.796. That is, whenever my observed T is less than this number, I will reject the null hypothesis. All right, because that will consider this is too small. All right. Okay, so where T is equal to x bar minus mu naught S over root n. I have to stress that these two, what's the difference between these two? The top one with capital letter T refer to a random variable. That means this is a random variable, so you can interpret as different samples will give them different value of T. So T can take many possible values, but the behavior of this T follows certain distribution. The last line, the lowercase t, referring to the realization. That means once you take a sample, all right, and you look at the value of this sample, that means you ask everyone in the sample what's the registration time. So you got a realization of the sample. All right. So in other words, you can compute, all right, the values. So you obtain a number. That's for t. If this number is less than minus 1.796, then you think that this what you see here is too extreme, because the chance that less than this number for a t distribution with n minus 1 or with 11 degrees of freedom is very small, only 5%. So now we compute with the data from the sample. Sample mean 42, sample standard deviation 11.9, so we got minus 2.326, minus 2.329. So this number, all right, is it too small? So if you have a computer or your calculator can calculate the t distribution, then this is the probability. The chance less than this number, this I call it the observed t-value from the data. And it is the chance less than what I observed is only 0.0199. You can use Excel to get this number. I think for the Excel, you just use t distribution, then type minus 2.329, and then the degrees of freedom 11, and then true. True means that we are looking at the cumulative distribution. 3 arguments for this function t dot dist. This is a command used in Excel. All right, minus 2.329 is this value, so we are asking to compute what is the probability less or equal to this number. With this follow a t distribution with 11 degrees of freedom. Okay, so just in case, if you don't have a computer, you don't have a calculator that able to compute the t values, the probability, then you have to consult using the old tools, which is the t-table. So the t-table, all right. So you look for this 11 degrees of freedom, and we know that, all right, greater than this number with 2.5%, greater than this number is 1%. So in other words, the t-table will tell you that for a t distribution with 11 degrees of freedom, this point 2.201. So the probability greater than this is 2.5%. So 2.718, this point greater than it is 1%. So 2.329 is somewhere between these 2 points. So the idea is that, okay, I cannot tell you what the exact p-value from this table, but I can tell you the range. This is an important technique. Okay, I cannot give you the answer, but I can give you a range of this p-value so that you can make your decision based on this information. So I know that the probability of greater than 2.329 is about between 1% and 2.5%. All right? So in other words, if I set my significance level at 5%, then this p-value is considered as smaller than the 5%, so I reject the null hypothesis. On the other hand, if I set my significance level at 1%, then the p-value is bigger than 1%, so I do not reject the null hypothesis. So now, so I reject or should I not reject? 1% I do not reject if I set my alpha as 1%. So if I set my alpha at 5%, I reject. So should I reject or should I not reject? So I go and ask my boss or my client, do you want to reject the null hypothesis or not? No, this is cheating. All right? So that's why I have to stress that we have to set the alpha, the level of significance, at the beginning without looking at the data. So you must set that. So in this question, what's the alpha I set? 5%, right? So I will make the decision based on the alpha that I specify at the beginning. All right? So in this case, I reject the null hypothesis. Okay? Okay, in fact, okay, so 2.329, the probability is between 1 and 2.5%, so minus 2.239, so it's between, again, less than it is between 1% and 5%. All right? So we reject the null hypothesis based on 5%. But on the other hand, you can also, using this O approach, that means called critical value approach. So I decide that whenever your observed t is less than this number, I reject the null hypothesis. Well, you got this number because I set alpha equal to 5%, and I know that the test statistic follow a t distribution with 11 degrees of freedom. Therefore, the chance less a random variable of t with 11 degrees of freedom less than this number with probability 5%. So now my value from the data, from the sample, is less than this number, so I reject it. All right? Okay. So now we move on to expand our scope. Instead of looking at the difference between, instead of looking at one mean, now our statement concerns about two means. All right? We are interested in looking at testing mu1 minus mu2. It doesn't matter whether it's mu1 minus mu2 or mu2 minus mu1. All right? This is, either one will do. But you just to be consistent. That means if you're looking at the hypothesis concerned about mu1 minus mu2, then you stick to that. Your test statistics, all this will derive based on the test hypothesis of mu1 minus mu2. Okay, so we start with simple, the simple way. So a simple problem. So we don't make it so complicated. We assume that we know sigma 1 square and sigma 2 square are known. In other words, we know the population variance. All right? So basically, the idea is that, okay, I have two populations. Population 1 and population 2. So mu1, sigma 1 square, mu2, and sigma 2 square. So we want to know the difference between mu1 and mu2. In fact, the most important statement is mu1 and mu2 are equal. This is what we want to find out. Of course, you can find out mu1 minus mu2 equal to 10, for example. Yes, this is another statement. But usually, the most common statement that we want to test is mu1 minus mu2 equals 0, or mu1 equal mu2. All right, so we assume that they are known. All right, and we also assume that the underlying distribution is normal. The underlying distribution is normal. If they're not normal, then we can still use these results, provided that your N1 and N2 are big. That means bigger than 30. All right. Bigger than 30 is considered big. It's just a rule of thumb. So it's not cast on stone rule. 29 you cannot use. All right. Or it just saying we use this rule when it's bigger than 30. All right. So we repeat what we did before. So if the statement is mu1 minus mu2 that we want to find out, so naturally we'll use x1 bar minus x2 bar, the difference of the two sample means. All right? Then look at the difference between this and this. All right? If the difference of these two quantities, the mean difference of two sample means and the difference of two population means, if these differences are big, are huge, then we suspect okay, in fact, it's equal to something. So let's make it simple, like equal to 0. So if this difference and this difference, all right, you must know this. What is this difference? This is specified under the null hypothesis. All right. You observed the data. So you have x1 bar. You observe the second sample. You have x2 bar. But you also have to specify what is mu1 minus mu2. Where we get this mu1 minus mu2? From the null hypothesis. From the null hypothesis. All right, so look at the difference and then divide by the standard error of x1 bar minus x2 bar. But what is the standard error of x1 bar minus x2 bar? Is sigma 1 square over n1 plus sigma 2 over n2. Take the square root. So that is our test statistics. All right? So now we have these problems. So we want to check. All right? So this is one way to produce the stew. And then the stew produced by this method has a strength, average strength, all right, from a sample of 20 with the mean equal to 29.8 KSI. All right. So we have this method to produce stew, and we look at the strength, and a sample of 20 of this stew made from this method has an average strength equal to 29.8. Then we have another method, gravitized stew. All right, we take 25 specimens from this method and can check their average strength. So the average is 34.7. So apparently the The second method seems to produce an average bigger. It's 34.7, bigger than 29.8. All right? But you cannot jump to the conclusion because the difference is about 5. But is it big or not? It's still, you still have to look at the variation of the difference. If the variation is very big, then the difference is not that considered that big. All right. So suppose we assume that the strength follow for the each still species follow a normal distribution. The first one with sigma 1 equal 4, and the second population with sigma 2 equal 5. Then does this data, all this information suggests that there's a difference between mu1 and mu2. All right. So in other words, we want to find out whether this, it did not say which one is bigger, which one is smaller. We just want to know whether there's difference between the mu1 and mu2. All right, so we use level of significance equal 1%. All right, so step 1, set up a hypothesis. So I must specify what do we mean by mu1 and mu2. So this referring to the average strength of those steel pieces that make from the different methods. And then we want to test mu1 different from mu2. So the null hypothesis mu1 equal mu2. That means the status quo. I assume that these two methods are the same to start with. And I look for evidence to prove that I will reject this one. Look for evidence to support my decision to reject this statement. All right, so step 2, set my alpha. We are told that alpha equal to 1%. Then step 3, set up my hypothesis. So this is the test statistics. But this is only a part of it. You still have to decide, all right, on what is the distribution. If you want to use the p-value approach and specify how to compute your p-value, whether it is greater probability. Okay, you have to say how to get the p-value. All right. In this case, is the 2 times minimum of two things: the probability of z less than minus z alpha over 2, or z greater than z alpha over 2. All right. For two-side alternative, you have to check from the data. All right. Calculate your z. All right. Such that the probability of less than what you, okay, I'm sorry. This is not alpha over 2. I'm sorry. Less than z observed. This is z observed. All right, I confused the two. All right, let me repeat. The p-value is 2 times the minimum of the chance that you observe a standard normal, because I believe that this follow a standard normal distribution. So this follow a standard normal distribution. So I look at my observed value. See whether my observed value is small or not, or too extreme or not. So I look at it. See one side, less than it, what's the chance? And I also see the chance bigger than it. All right? So if it is extreme, then one of these values, one of this probability must be very small. All right? Let's say if I observe, after I take the sample, I calculate these two, and these are the difference under the null hypothesis is 0. I know all this, so I can compute it. Suppose it turns out that z, from the data I observed, z equal to 3. All right? Z equal to 3. Is it very extreme? What's the chance that a standard normal have a value greater than 3? You have any idea? You must practice more so you know that for standard normal, the chance between 3 and minus 3. What is this chance? 99.8%. if I remember right. It's 99 point something percent. So what does it mean? It means this one is very small. Less than the two sides add together is less than 0.5%. So what does it mean? So the chance of greater than 3 is very small chance. So what does it mean? 3, what you observe is really considered as very unlikely if the null hypothesis is true. So most likely, mu1 is bigger than mu2. That's why you observed the test statistics is so big. All right? So 3, how do I know 3 is big? Because I know how this z, all right, the random variable z behaves. It follows a standard normal. So now I look at my value, which now to be 3, for example. Then it's considered extreme. And what makes it so extreme, so unlikely to see 3? Under the null hypothesis, mu1 equal mu2, right? So most likely this hypothesis is wrong. That means mu1 does not equal to mu2, all right? So I reject this statement. But if you see that your observed value is equal to 1, all right, then is it likely? Yes, it's likely that you see, because the chance that you see a 1 or bigger than 1, all right, the probability is quite big. All right, it's at least 10%. All right. Okay, so this is my test statistics, and this is the critical value approach. Since alpha equal 1%, so I decide that okay, this is the value. So in other words, this is 2.5728. The chance bigger than this is 0.5% chance. So if you're, based on data, you compute this z, and turns out that it is bigger than this number, I will reject the null hypothesis. But how about if, based on the sample, I calculate the z, it turns out it is -3. Should I reject? Yes, because for two-side alternative, you have two-side region. So -2.5728. All right? So for two sides, you set two critical region. Bigger than 2.57, you reject. Less than minus 2.573, you also reject. All right? All right, so this is my critical region. All right. So in step 3, you have to decide on the test statistics and your decision rule. So based on the critical value approach, I specify the region for which you should reject the null hypothesis. Or you specify what is the p-value. P-value for two-side alternative is the probability of the standard normal or the distribution z, all right? This z, this is the z which suppose follow a standard normal less than what you observe or bigger than what you observe. All right? And take the minimum, but multiply by 2. All right? So this is the z. Okay, step 4, now we make use of the information from the samples and calculate our test statistic, and turns out to be -3.652. This is really, really, really very extreme. The chance you see something less than this number is very, very small. All right? So the p-value is 2 times the minimum of greater than -3.652 and less than -3.652. All right? Whether you are extreme or not, you cannot just look at one side. You have to look at both sides. All right? So you pick the minimum of the 2. All right? So in this case, the p-value is 0.0026. So we decide to reject. All right? So the rejection, the decision to reject it, either you use the critical value approach, that is z is falls in the critical region because it's less than -2.73, or the p-value, all right, is less than the level of significance, which is 1%. So we reject the null hypothesis. All right? Okay, so now what happens if sigma 1, sigma 2 are not known? All right? And if the sample size is big, then we can still proceed as if it is normally distributed for the test statistics. All right, so here is an example. So we have, again, we want the thermal conductivity of the materials, all right, the sulfur concrete, all right, try to be as small as possible. And we have two ways to manufacture the concrete. One is, one type is concrete aggregate, the other was no fines aggregate. All right, so we look at the difference between these two. All right, so here, this is the summary of 35 concrete slumps and 35 for those from non-fines grade aggregate. Okay, so these are the sample mean conductivity, x1 bar, this is x2 bar, this is S1 square, and S1 and S2. All right. So, so does this information suggest that the grade concrete, so in this case is 1, so it's mu1 minus mu2 greater than 0. So that is my alternative. I want to know whether mu1 is greater than mu2. All right? So use significance level 1%. So here, so I want to test mu1 equal mu2 against mu1 minus mu2 greater than 0, alpha 1%, and this is my test statistics. All right? I don't know sigma 1 square, I don't know sigma 2 square, so I replace it by the sample variance. And what is the distribution? So the distribution is approximately normal, All right? Okay. This, if it's sigma 1 square over n1, sigma 2 square over n2, then this will follow approximately normal using the central limit theorem. But we don't know sigma 1 square and sigma 2 square, so we estimate it by the sample variance. So this one we use, again, this is called law of large number. So if your sample size is big, your S1 square should be very close to sigma 1 square, and S2 square should be very close to sigma 2 square. So in other words, if your sample size are big enough, then you replace the sigma 1 by its estimate and sigma 2 by its estimate, then the difference is not too much. I mean, so the error, I should say error, not difference. The error should not be too much. So we still consider it follow approximately normal. All right, so that's why the critical value we use is from the standard normal distribution. All right, so we believe this follow approximately standard normal, so we pick up this value, which is 2.326, so the chance of bigger than it is 1%. So if I got my data, I compute this one, if it falls here, critical region, I reject the null hypothesis and favor the alternative. That means I believe that mu1 minus mu2 is bigger than 0. But if the observed set is somewhere here, then I make the decision I do not reject the null hypothesis. That means I still believe mu1 and mu2 are the same. All right, so this is my critical region. So Z is the realization of the random variable, the test statistic Z. So use the data, I compute Z equal to 3.335, which from a normal distribution, this is a very extreme value, very huge value, because the chance of greater than this number is very small for a standard normal distribution. So this is the p-value, 0.00043. So what it means is that if mu1 really equal mu2, then the chance that you see the observed Z value equal to 3.335 is very, very small. All right, chance see something more extreme than this value. You see, you cannot just look at what's the chance that I got my test statistic equal to 3.334. We cannot just look at the probability of the random variable equal to 3.335. This probability is always 0 because Z is a continuous random variable. So what we ask is more extreme. So this is considered extreme. This is also considered as extreme. All right. What I mean is to check whether it's extreme or not. That means I check what is the chance that I'm a big number. So check what's the chance that it's bigger than me. So if whether I'm a very small number, so I check what's the chance that it's less than it. So 3.335 is not small number. It's a big number in terms of a standard normal random variable. All right? This one? Which one's negative? More extreme can be bigger, can be smaller. We are looking at one side or two side alternatives. We're looking at this one, right? So we expect a big number. So the question is whether it's big or not. What we observed here, whether this number is big or not. So we ask these questions. Right? Let me repeat. I used the word extreme. I did not say it's big or small. Extreme can be big, can be small. All right? So in this case, I see my value, observed value from the data, from the sample, is 3.335. So ask myself, is this number big or small? So it's too extreme or not. But because of the alternative hypothesis, we're interested in mu1 minus mu1 bigger than mu2. Therefore, extreme means that bigger than what I have. Because I expect under the alternative, I see a big number. Now, if I change my alternative hypothesis to testing mu1 minus mu2 less than 0, then this number is not considered as extreme because the chance that Z less than 3.335 is equal to 0.99957. So in other words, what I see is not considered as small, all right? Because the chance less than it is almost 1. So this is not a small number. So I will not reject the alternative hypothesis. If the alternative hypothesis is mu1 minus mu2 equal less than 0. All right? So because it's one side, so you don't see this part. All right? We don't have this one because it's one side. And we want a bigger side. Mu1 minus mu2 bigger than 0. If mu1 minus mu2 bigger than 0, I expect x bar 1 minus x bar 2 should be bigger than 0. Much bigger than 0 if the difference is large. So I minus mu1 minus mu2, which is 0, under the null hypothesis. Remember, all the computations are based on the assumption that the null hypothesis is true. You see, the whole idea is that, okay, let's look at H0 is true. I try to look for evidence to say that, okay, if this is true, I won't see that. So, okay, in other words, let me give a very practical example. Okay, so if I see someone stay in, let's say, a HDB 3-room flat, then what is the chance that he is a multi-millionaire? The chance is very small because if he is rich, all right, then he may likely to stay in maybe condo or landed properties. All right. I'm not saying that no multi-millionaires stay in HDB flats, but the chance is that it's likely that if it's a multimillionaire, then it should stay somewhere else. So I don't see it stay in a HDB set with a high chance. So the same apply here. If the null hypothesis is true, so I see something that is not very likely, then I believe that the null hypothesis is not true. So I make a decision, I reject the null hypothesis. Right. But what is considered extreme, it depends on your alternative. That's why define the alternative is very important. Okay, so we make the decision, we reject at 1%. All right? All right. How about if the variance are not known but equal? All right? Now, so in this case, we need the population to be normal because we are going to derive the test statistics, and based on the assumption that sigma 1 square, sigma 2 are not known but equal, I have to use this information. So that's why these two are the same, let's call it sigma square. So I have to estimate this sigma square from the data. So we discussed it before, we use this n1 minus 1 s2 square and n2 minus 1 s2 square over n1 plus n2 minus 2. We use this to estimate sigma square. I weigh the average of s1 square and s2 square. All right? So assume small samples and population is normal. Then, okay, so this is an example to illustrate. So we have this, two teaching procedures. One is the conventional classroom procedure. The other one is the programmed materials. So we have these two teaching methods. Okay, we apply this to two different groups of students. One is 12 students, the other one is 10 students. Okay, at the end of the semester, we sit for the same exam, and this 12 students group under the traditional method has an average equal 85 and standard deviation equal to 4. And the other group under the programmed materials approach, 10 students, average 81 and standard deviation 5. So we want to test whether the two methods are equal. Okay, I think to be more accurate, we want to find out whether they are different or not. And different in terms of what? In terms of their score, the average score. All right? It should be the different that we are interested. If you believe that it's equal, why bother to do any testing? So we just use either one method. So what we want to find out is that whether there are differences among them. And we use 10% significance level. Furthermore, we are told or assumed that the data are normally distributed, or at least approximately normally distributed. Not only that, we are also told that the variances of these two, the variance of the score, the exam score, under these two different methods are the same. All right? So we set up the hypothesis. We want to test mu1 equal mu2 against mu1 does not equal to mu2. All right. Then we set alpha equal to 10%. This is my test statistics. All right. x1 bar minus x2 bar minus mu1 minus mu2. So this is an estimate of the standard error of x1 bar minus x2 bar. It's supposed to be sigma square 1 over n1 plus 1 over n2. And we estimate sigma square by SP square, where SP is the weighted average of the two sample variances. Right? So basically it's still the same thing, except we make a minor modification because now we know that sigma 1 square equals sigma 2 square. So I have to combine the two estimates using the weighted average method. And the next question is, what is the distribution of this T? All right. So this one follow a T distribution with N1 plus N2 minus 2 degrees of freedom. So this is all the information that we have. So the next is just to decide on the critical region less than minus 1.725 or greater than 1.725. Then it's considered as a rejection regions. All right? And so we just compute it, and it turns out that the SP square is 20.05. So I substitute in and calculate the T is 2.086, which is, where is it? Okay. So I also compute the p-value. All right, the p-value. So it's a T distribution with 20 degrees of freedom greater than this number or less than this number. I take the minimum of these two probabilities. So whether I'm extreme or not, I look at my left-hand side, what's the chance that it's bigger than me from a T distribution, and also look at my left-hand side, see what's the chance that it's less than me, that's my value, 2.086. So I take the minimum of the 2, and then multiply by 2. It's turned out to be 0.05. All right, so the observed T value is 2.086, which falls in the critical region. So we reject it at the 10% level of significance. All right, so we conclude that the two methods are not different. All right, the level of significance is 10%. And the p-value is 0.05, which is less than 10%. So we reject. We do not reject the null hypothesis. Now, we have what happens if my alpha is 5%? So I reject or do not reject? Theoretically speaking, we do not see such situation. All right. So, because the probability of a T, all right, greater or equal to 2.086, all right. Oh. All right. Okay, what I'm trying to say is that it's seldom to be exactly equal to 5% for the p-value. Here, there's some kind of approximation. So you just make your decision based on whether it's bigger than 5% or less than 5% and want to have a more accurate value. So like this one is round to 3 decimal place. If you take more decimal place and check with the critical value, then you may be able to decide on it. But if you really cannot decide, so you just report what your decision is. All right? So it's on the borderline. So you reject or do not reject is still acceptable. All right. So what to do? In practice, what you should do? Collect more data. All right. So what I mean is that if this is the only information that you have, and it happens that your p-value turned out to be 0.05, and if you set your level of significance 5% at the beginning, then you have this problem. All right, so you just decide on whether you reject or do not reject. All right, but in practice, maybe you still have to make the correct decision. Borderline is not, on the boundary is not good, so you just collect more information, collect a bigger sample or another samples. All right, then to do it again. All right. All right, there's this pair data. So in this case, we have 2 samples, but they are paired. All right. So this is an example. So we have a sample of 12, or is the iron samples. Okay. So we split each samples into 2 parts. One under determine the percentage of iron. So one under method 1 and the other half under the method 2. So in other words, this particular sample, I divide it into 2 parts. One apply method 1 to determine the percentage of iron, the other apply method 2 to decide on the percentage of iron. All right? So they are considered as pair because both the percentage of ions are from the same unit, from the same from the same sample. All right. So altogether, I have 12 of them. 12 of them. All right. So these are pair sample. So what we're interested is not mu1 minus mu2, but it is the difference. All right. The difference. The D. We are looking at the mu D. Mu D. Whether this one equals 0 or not. D is equal to x1 minus x2. All right? Okay, so these are the percentage. So these are from the sample 1, sample 2. So we look at the difference. It doesn't matter whether it's x1 minus x2 or x2 minus x1, so long as your alternative or your null hypothesis and total hypothesis are set accordingly. So for example, I believe that the percentage is determined by method 1, okay, is systematically larger than, so if this is what I believe, then my test, the alternative is to test the difference. If I use x1 minus x2, then I test whether mu d is bigger than 0. Because my difference is x1 minus x2. Okay, so I test mu d, all right, bigger than 0. But on the other hand, if I define my difference as x2 minus x1, then my equivalent to this will be mu d less than 0. If I believe that this method has an average less than the other methods. All right? So basically, we just reduce it to one sample. So now we are saying that the method 2 use a higher average. So if I consider x1 minus x2 as my difference, so now I'm looking at mu d less than 0. All right? Because that means this is systematically higher than this one, so I expect a negative number. So we expect d is less, or the average of d should be less than 0, if I believe that the yield of method 2 is higher than method 1. So we assume that the difference follow normal distribution and use alpha equal 5%. So first of all, I define that mu d is the difference between 1 and 2. So in this case, we are looking at d, which is x1 minus x2. All right? The method 1 percentage or yield compared with the method 2. And the alternative is mu d less than 0. That is, we believe that this one is bigger, this one is large, while this one is small in general. So that's why we expect the mu d is less than 0. So set up your alpha, and the test statistics will be, because now basically you have D1 up to D12, 12 differences. All right? These are the differences. So we just take the average of all this D and then minus mu D. This is under the null hypothesis 0. Okay? And then over the standard deviation of all this D divided by square root n. And this follow a T distribution with n minus 1 degrees of freedom. So we will reject the null hypothesis. Oh, yeah, the critical region is here. All right, less than minus 1.796. All right, because we look for small values of the test statistics. Why? Because we believe that the D bar should be, we expect D bar to be, it should be negative, because mu D under the alternative is negative. All right, so applying, get the data, we compute all this, and then the T statistics, observed T value is minus 2.16, which is, has a P value equal to 2.7%. All right, again, this one I use the information that is between two values. All right, between these two values. this 2.156 is between this value and this value. The chance bigger than this value is 5%. The chance bigger than 2.201 is 2.5%. So this bigger than this value is between 2.5% and 5%. Or in other words, less than this value with a probability between 5% and 2.5%. So our alpha, our significance level is 5%, so we reject the null hypothesis. All right? Or the p-value is less than 0.05, so again, we also reject the null hypothesis. So you just have to do one of this approach. Either you use p-value or use the critical value. Unless the question states that you must use this p-value approach, then you have to use the p-value. It says that use the critical value approach, then you have to use the critical value approach. All right. Then next, we look at the hypothesis concerning about the variance. All right. So now it's a different story. We need to assume normal. So for this case, we assume normal distribution for the population, and we assume that the data, the random sample, are from a normal distribution, or at least an approximately normal distribution. With, of course, sigma square is not known, otherwise we don't have to do the hypothesis testing. And it should be mu is unknown. Mu is unknown. All right? Mu is unknown. What I mean is that, of course, sigma square is not known. If sigma is known, if sigma known to be 1.2, then you want to know whether the statement mu equal to 1.5 is correct or not. Of course, I know the answer. Sigma is 1.2. How can it be 1.5? So no need to do any testing. I can tell you, you're wrong. All right? The problem is that we don't know sigma. And based on the sample, we want to decide whether sigma equal to a certain value or not. All right? So what we assume is that we don't know mu. And in fact, this is the usual case. You will not know what mu is in general. All right? So let's assume mu is not known. Then from last chapter, we know that this follows a chi-square distribution with n-1 degrees of freedom. All right? In fact, this follows a chi-square distribution with n-1 degrees of freedom. Why suddenly sigma square becomes sigma naught square? What's the difference between these two? One with the denominator sigma square, the other one with the denominator sigma naught square. What's the difference between the two? With the denominator sigma square, it applies to any problems, so long as the sample is from normal with mean, mu, and variance sigma square. But we are now trying to test the hypothesis, sigma square equals sigma naught square. So I want to know how this quantity, n1 minus 1 s squared over sigma square, behaves when the null hypothesis is true. So null hypothesis true means sigma square equals sigma naught square. So I substitute sigma naught square into sigma square. This is, I have to stress, this is under the null hypothesis. We are interested to find out how this quantity n1 minus 1 s squared over sigma square behaves when sigma square equals sigma naught square. All right? So this is our test statistics. So if the alternative hypothesis is greater than sigma naught, okay, so I will look for this value. This value is for which greater than this number with alpha. But if my alternative is sigma square is less than sigma naught square, then I will look for this value such that it's too small. And this value is given here. All right? So the chance of less than it is alpha. Greater than it is 1 minus alpha. All right, I have to, this is what I mean by this number. All right? Well, if it's two-sided, then I have to take both. Either this one or this one is true. And then I cut change alpha to alpha over 2, change 1 minus alpha to 1 minus alpha over 2. So in other words, if I see my chi-square, what's my chi-square? My chi-square is n1 minus 1 s square over sigma naught square. So this one, once you take a sample, calculate this one. If less than this, then we reject. Or greater than this one, we reject the null hypothesis and favor this alternative. So let's look at an example. So this car battery manufacturer claims that the life of his battery is approximately normal with a sigma equal to 0.9. This is his claim. So I want to check. So I take a random sample of 10 batteries and find out that S equal to 1.2. So can I, based on this one, reject his statement? So I want to know, if sigma is really 0.9, how likely I will see something more extreme than what I see for the sample standard deviation, 1.2. All right? So we also specify the alternative. This is to see whether sigma is bigger than 0.9, while the null hypothesis is sigma equal to 0.9. All right? By the way, this sigma bigger than 0.9 is not because I look at my standard deviation 1.2, which is bigger than 0.9, so I set my alternative as sigma bigger than 0.9. You shouldn't do that. All right? You should set your alternative before you look at your data. Okay, we use alpha equal to 5%. All right, so follow all the steps. Define our alternative and null hypothesis. So sigma square equal to 0.9 square against sigma square bigger than 0.9 square. Alpha 5%, and because n equal to 10, so I look for this value. So I look for chi-square 9, degrees of freedom. Look for this point such that the area, and this is 16.92, and the area bigger than it with probability 5%. So this is how I get this number. This is the number such that a chi-square with 9 degrees of freedom, random variable, will be bigger than this number with 5% chance. So our critical region is this part, greater than 16.92. All right? So now, we look at our data and compute it. Chi-square equal to 16, which is smaller than, what is the number again? 16.92, just slightly less than it. All right. So 16.92, greater than it is 5%. So this is my critical region. And what I got, my observed value is 16, which is here. So I do not reject the null hypothesis. And you also can get the p-values. So if you use Excel, the statement will be chi-square 16. This is the observed value. The degrees of freedom is 9 and true. All right. This will give you this part of the area. So in order to get this part, I have to 1 minus this. All right. So you will get 0.0669. But if you don't have a computer, you don't have a calculator that able for you to calculate this probability, then you will have to look for the table. So look for a chi-square distribution with 9 degrees of freedom. Look for two numbers, and we find that this 16 is between 5% and 10% value. All right? So we do not reject the null hypothesis. Okay, for ratio of variance, that means we are interested in sigma 1 over sigma 2 square. Test whether they are equal to 1 or not. All right? So again, we need normal distribution, and we assume that mu1 and mu2 are unknown. All right, so here's an example. So, we have compare the precision of a measuring device. All right. So variability of grading practice of one teacher is maybe different from the others. All right. Or a process, the consistency of one process compared with the others. So all this involves the variations. So marking by teacher 1 and marking by teacher 2, the marking of teacher 1 may be the variation is very small, while the other teacher maybe the marks have a big variations. So we want to find out whether the variations are the same or not. So this is an example to illustrate the use of comparing or whether this is true or not. So we want to test this one. All right. So okay, so we draw two samples, independent sample, and this we know that this is our test statistics. All right. So under the null hypothesis, basically we just look at S1 square over S2 square. And this follow F distribution with N1 minus 1 and N2 minus 1 degrees of freedom under H0. If in general this is true, but under the null hypothesis, these two cancel out because they are equal. So we know how it behaves. All right. So this is our test statistics for testing sigma 1 square equals sigma 2 square. All right. And the alternative, same thing. Sigma 1 greater than sigma 2. So we look at when the observed value greater than this number. Oh, okay, this is a typo. It's less than. This one should be less than. All right. Then you have so you have this value. All right. This is this value. But just recall in chapter 6, this is the same as 1 over f n2 minus 1, n1 minus 1 alpha. All right. There's a relationship between these two. All right. For two sides, it's like that. All right. So let's look at this example. So we have this two different laminate materials, and we have 11 pieces from material 1 and exposed. All right, try to check its wear, and material 2 is similarly tested. So the depth of wear is observed. So each piece we measure how the depth of wear, all right, how much it decreased the thickness. So for the sample 1, the average is 4. The standard deviation is 4 with 85 units. So N1 equal 85 and S1 equal 4. So similarly for second material or second sample, N2 equal 81 and the S2 equal to 5. So assume that the data are approximately normal, all right? Then we test whether the variants are the same. So this is my null hypothesis, and my alternative is that they are different. They are different. Equal to 1, and this one does not equal to 1. All right, use alpha at 10%. All right, so set up the hypothesis. This is the hypothesis, and this is the level of significance. And then we find the critical values. Because it's two-sided, I have to get one number and also the other number. So in other words, I look for these two numbers. This is 3.35, greater than it, 5%. Another number, 0.326, less than it is 5%. So these two are my critical region. And how to get this number? You just take 1 over f, swap the 2 degrees of freedom, and then look at 5%. All right. So in other words, this denominator is the value. Now is f, instead of 10x, is x10. And look for this number. So that this is 5%. All right. And so this is my critical regions. So from the data, I calculate the ratio, which is 0.64. All right. The ratio S1 over S1 square over S2 square is 0.64. And this 0.64 falls outside the critical region, or it falls in the acceptance regions. If it's less than 0.3 something or greater than, what is it? Greater than 3.35, 0.26 and 3.35. All right. So this number is not less than this, 0.326, and it is not greater than 3.35. So it falls within the acceptance region. So we do not reject the null hypothesis. Okay, sorry for the rush. So we finished this chapter. Last page, right? Yeah. Okay, so you should be able to do your tutorial for next week. All right. So next Monday we will do a revision. All right. Up to you to come. All right. So we basically finished all the lecture notes. So we stop here.